I'm going to run through now an example of an experimental design. So this is a moderately complicated experimental design. It involves blocking and blinding. So blocking and blinding can improve your experimental design by minimizing the amount of bias you have, and particularly dealing with confounding variables, and improving the accuracy of your results. So accuracy means making sure that you get the correct answer. It's not precision. And the best design will give you the best chance of having reproducible research. So blocking is a way of dealing with confounding variables. It was originally designed when they were doing plant experiments at Rothamsted Research Institute. So there you have a field, and the field's going to have different soil properties depending on if it's uphill or downhill. So what you do is you plant your crop in, let's say, 2 blocks at the top of the hill and then 2 blocks at the bottom of the hill. So you make sure that your blocks at the top and bottom of the hill are both paired to each other. So you have the same crop planted in one at the top and one at the bottom, and alternative crops in the other block. This way you take into account any variation in soil type and remove that confounding variable. So stratification, you can make it as complicated as you want, but the more blocks you have, the more complicated your design becomes, and the more more experiments you have to carry out, the more participants you need. So treatments are assigned within the groups to keep the confounding variable fixed. So you have different treatments within plots of similar soil types. Now blinding is used to avoid bias from the experimentalists. Now this is particularly important in clinical trials where people can skew the experiment with the best of intentions. So you might only give, you're taking part in a new drug trial, and you might only give the drug to the most severely affected patients that you have. Now this is going to skew the trial. They have to be randomly selected amongst all the different patients. It might be that you don't pick the sickest, but you pick those with the best chance of surviving. So the drug company naturally wants you to pick the ones that are going to show the best possible recovery from this, and it doesn't want to have a large death or dropout rate. So there are different agendas and different pressures depending on where your perspective is coming from. You see this in the Lind experiment with scurvy, where he singled out the 2 sailors who already had cramps in their hams for the seawater treatment. So he didn't actually administer a fair test when he was looking at the use of citrus fruit. If I was doing teaching, then what you could do is put the students that you prefer into one teaching method as opposed to the students that you're not so keen on. So whenever there's choices of an experimentalist, you have to make sure that it's completely randomly assigned. And education research is particularly difficult because you might choose one particular teaching strategy and give that to the well-funded and schools in richer areas, while giving the standard control poorer teaching experience to schools in poorer areas. Now the experiment that I've chosen to do as a demonstration is one involving toxicity. So it's going to involve 16 rats in total. 8 are exposed to a toxin, 8 are going to be the control group. So they are given something, a preparation, but it's inert and not toxic. You have to make sure that both the treated and untreated group are given something. Now the experiments are going to be performed by 2 different researchers, Anne and Bill, A and B. And what you ideally want to do is order all your experimental supplies from the same company. But because of bad luck, when it came to ordering the experimental kits, half of them have come from one supplier and half of them have come from another. So these are Agilent and Illumina, which are real companies. So this gives us some potential experimental design, of which I'm going to suggest 3. There are more. So design 1, I give Anne all of the sachets, the food supplements which have the toxin in, and make sure that she exposes the rats to toxin, and I give her all the Agilent kits to do the processing of the data and the collection of the data on the samples. Whereas Bill has all the control samples and Bill uses all the Illumina kits. So what's wrong with this design? This is pretty much the worst design you could possibly do, because it doesn't just try to reduce confounding variables, it actually adds confounding variables. So you can't tell if there's a difference in the response of the rats to the toxin against the control group, whether it's because of who prepared that particular sample. So if Anne and Bill are different in their skills as experimentalists, or if there's a difference in the reagents between Agilent and Illumina. You've now confounded any possible difference between the treatment and the control with these other factors. So that's a bad design. The second design is a much more effective and good design, and this deals with both of those issues together. So Anne chooses 8 rats at random, treats 4 of them with the toxin, and 4 are left untreated or given the inert treatment. She uses 2 Agilent kits and 2 Illumina kits with the toxin, and she uses 2 Agilent kits and 2 Illumina kits with the control group. Bill follows exactly the same procedure. Now this is a good design in terms of blocking. You've removed the test kits and the experimentalists as confounding variables. So now you can see if there's a genuine difference between the rats that are exposed to the toxin and those that aren't. But there's still one thing that you could do better, and that is, do the experimentalists have favourite rats? So most clinical trials are done by blinding, and they're usually double blind. So the rats, because they're not sitting there going, oh, that looks like toxin, oh, that looks like the control group, that looks like a placebo. They can't distinguish things, that they're always blind because they're not able to respond. So when you do medical experiments, the patient is blind. They don't know if they're getting the treatment or the placebo. But you make it doubly blind by not allowing the doctor who's administering the placebo or the drug to know that either. So Anne chooses 8 rats at random, treats them with unlabeled compounds that she is given. 4 contain the toxin, 4 contain an inert substance. When it comes to preparing the samples, of the 4 that contain the toxin, 2 are already matched with Agilent, 2 already matched with Illumina, and the same for the ones that are inert. And Bill follows the same procedure. So they're unaware which ones get the treatment and which don't. This is the best possible design. So blocking has removed any confounding effect of which kit is used and which researcher does the experiment. And blinding has been used to remove any experimental bias. This is the best possible experiment and the one that is likely to give the smallest amount of bias and be the most reproducible.